Hi all, I am Chandrasekhar Vorganti. So today I am going to present our work, Teacher-Student Collaborative Knowledge Distillation for Online Signature Verification. So online signature verification is a time series data which is sampled at regular intervals while a user is signing on a digital device. So current advances in deep learning technology catalyzed the state-of-art frameworks for challenging domains like computer vision, speech recognition, etc. So we are interested to adapt deep learning-based frameworks for online signature verification. In order to deploy online signature verification frameworks in edge devices, low-end devices, the main problem is the huge trainable parameters and hard to deploy in real-time systems. So, to adapt deep learning into online signature verification for improved performance, we propose an online signature verification framework made up of teacher-student collaborative knowledge distillation, in which we train a teacher network results in an efficient deep representative feature learning. And we distill the knowledge from teacher to a lightweight student, which consists of a single convolution layer. So we evaluated the framework with three widely used data sets, and the model achieved the state-of-the-art performance in various experimental categories. So here, so even though the fact that transformer variants are powerful and best suits in effectively learning the long-term patterns, a transformer-based online signature verification remains unexplored in the literature. The massive number of trainable parameters results in extremely high training and inference cost. Hence they are unsuitable. The frameworks which contains the transformers are unsuitable for low power resource constrained devices. Hence, to reap the benefits of transformer architecture in online signature verification, so we have proposed this model. So our contributions are: we successfully applied transformer architecture to online signature verification because the transformer consists of encoders consist of the self attention mechanism, so which is critical element in learning long term spatial relationship of the samples of a signature, means the sampled elements of a signature. Second, we used a, um, a teacher-student based on knowledge distillation technique, which involves the transformer-based teacher network and distilling the knowledge from a teacher to a single convolution layer, lightweight CNN network. And we did a lot of experiments, uh, which confirms the efficiency of the proposed framework. So this is the architecture where we have used the model. So initially, the 1 cross 100 is the features extracted from the sample time series data for each signature. These 100 are the statistical features. In order to preserve the time ordering and the positional ordering of the data, we perform the time embedding and positional embedding, which results in 3 cross 100 vector. 3 cross 100 vector is feed into the transformer network and the convolution block. So here the attention layer, encoder consists of attention layers. So in each attention layer, there exists self-attention nodes. Okay, and the output from each self-attention node are concatenated together and passed on to a dense layer. Finally, it passed on to dropout, normalization, convolution layer, and normalization layer, which is 100 comma 3. That is the output from this particular layer. In case of convolution layer, also 100 cross 3 is passed as input to two convolution blocks, and finally the output is fused. The output from both the transformer and the convolution layer are fused together. The CNNs are efficient in extracting the short-term dependencies, and the transformers are efficient in extracting the long-term dependencies. By fusing both the features, it results into a hybrid transformer CNN-based feature set, which we feed into the dense layer for classification as Genina 4G. If you look into the main architecture, that means the self-attention mechanism, so the time embedded feature vector we pass on to the dense layer, and the output from the dense layer we feed the output from the dense layer is a query. Similarly, that same feature vector we pass on to a dense layer, and these dense layers are used to multiply the feature vector with the weights. So dense layers are used for the weight learning mechanism through backpropagation, and the output is keys. Similarly, the value also we feed into dense layer, and the output is a value vector. So we perform the standard set of operations like mat multiplying the query key, then scaling, then softmaxing. Similarly, the mat multiplying the value and the combination of Q and key results into attention output. This attention output is the output from the each self attention node. So like that, we are using a set of 12 attention nodes, and the output from each attention node is concatenated to form a 100 comma 3072. In order to reduce the dimension of the network, we use 100 comma 3 dense layers in order to reduce the computation and storage power. So this is how the transformer works. Now, if you see that the teacher, which is a transformer based, the vanilla, if we use a simple vanilla CNN, it contains 2 lakhs parameters, and we used a student of only one convolution layer. So if we use a transformer plus convolution, that's what I have explained in the above diagram. It requires 1 lakh 18,580 parameters, whereas the teacher requires only 3,266 parameters, which reduces the number of parameters by 97.25%. Okay, so now if you see that, yeah, so this is the student architecture, where we distill the knowledge from the teacher to a single student network and flatten finally a class softmax layer. So this is all the formula. If you see that, we evaluated our model with three data sets. So here if you see that, in case of MCYT data set, the proposed model, the teacher student based online signature verification, the student able to achieve the 12.42 ER with simple 3266 parameters, whereas the second best framework requires 2 lakh parameters. Similarly here also, a framework which results in best equal error rate in case of skill 10 category, it requires 35,000 parameters, whereas the proposed model requires only 3266 parameters. Okay. Similar is the case with SVC and SUSI datasets. Thank you.